Okay, optics. Just just know that I'm not really good at optics, and I have not done ray optics for a long time. So yeah, I'm pretty much a beginner, like you people. Okay, so let's start. In chapter exercise one, what is the minimum height of the mirror required for a person to see his image? Why did they give us the answer? I don't know. Isn't it supposed to be okay? Okay, yeah, understandable. It's half the height because if you have a person like I don't know, it's looking like a stick, but if this is the person you have his eyes at this level or something, he wants to see his feet. His eyes, I mean, okay, his eyes are almost at the top of his height, right? Yeah, almost like that. So if he wants to see this thing, so here's the reflecting surface. We don't know what part of it is actually what we're looking for. Um, but yeah, this will be having an image like this. So just mirror this, right? And then that means this is the line of sight that he will need so that actually he can see this. And then for this to happen, of course, like you should have a ray coming from here and then leaving it so in this direction such that you can see. So there are going to be like multiple parexel, sorry, multiple rays, so like something like this, and all of them leave such that they appear to come from here, right? And that's why it must be half the height because uh right, this kind of diagram should work, and that's why. Yeah, so what would happen if it's not half the height? So if it's something less than that, so it's going to be like this, right? Still what will happen is that uh, the image will definitely be formed over here, but now what's happening is that all of these rays, well, they have to be at least hitting this height so that they can get reflected, and that means the area when you can actually see this image is above this line, and that's bad for us because his eyes are lower than this area. That means it has to be half the height at least. Okay, second, if a mirror is rotated by angle theta, by what angle does the reflected ray rotate? So they're saying it's 2 theta. Let's see. So you have some incident ray like this, and then you have this reflected ray. Yes, so since you're rotating a mirror anyway, you're also kind of like rotating the normal. So right now what's happening is like, okay, these angles might be alpha or something. So these angles are alpha, and then you rotate by theta. So now this becomes like alpha minus theta. Or you can rotate like this. Doesn't really matter. So yeah, it's gonna make it alpha minus theta, and then right, because it's getting reflected. So now the mirror is something like this, right? So it's gonna be like this. So this angle is going to be sorry, this is not alpha minus theta. This thing is theta. This thing is alpha minus theta. So this whole thing must be alpha minus theta, right? Yes. So this angle was already theta. So this angle must be alpha minus 2 theta. But then this whole thing was alpha. That means this is 2 theta. So your image went from here to here. So it yeah, it changed its direction by 2 theta. That's why, yes, that's the answer. Okay, in chapter exercise 2, where is it? Spherical mirrors. Yeah, I mean, all this geometry that they did, it was actually unnecessary. You could have just done, you know, coordinate geometry, and right, that's the way I did it. Image tracing. No, I won't be drawing any ray diagrams unless you ask me to. And then you've got these, of course. I just hate this, you know, classification of when it will be bigger or smaller, but still I just read it. What are they saying? So for a concave mirror at focus f, we know it's going to be an infinity because that's the definition of the focal point, right? Between f and c, diminished, real, and inverted. Yeah, right, because this from c to the mirror, that's our normal. So over here, all of these rays, but at the focus, what was happening is that these diverging rays, this would try to converge it, but it can't converge it enough. It just goes parallel, but now it can converge it. So these will actually go somewhere over here. So this is where it will form, right? Yes. So since both v and u are negative, and for a mirror, our magnification is just negative v upon u. um, your magnification is actually negative. That means your image will be inverted, and it's real, of course, because these rays are actually going through that point. Then beyond C. So wait, what beyond? Oh, sorry. Between F and what are this? Yeah. So between F and C. Wait, where's the? Sorry, that's the image. Oh, sorry, I was thinking of something completely else. They're talking about the object. So when it's at infinity, of course, it's going to form at the focus. This is a no-brainer, really. And then when it's beyond C, so it's not infinity, but it's at some distance more than C, then it's going to form between C and F. Why does that happen? Once again, when it was at infinity, this could converge it to the focus, right? But now these are actually kind of like more diverging than usual, so it can't converge it enough. It will converge it to this point, but then why should it be inside of this curvature point? Because so from this center of curvature to this M point, that's our normal, right? And that's why it cannot be going beyond this, because that would make no sense, right? Yeah, it has to be a reflection, so that's why it's like this. Okay, understandable. And then they are saying it's real and inverted, right? So once again, v and u both are negative, so that's why inverted, and it's real because passing through it. Then you got at C, same size, real and inverted, right? So obviously, I mean, like at C, what's happening is that all of these rays, so just talk about this B point, it's at the center of curvature, so all the rays are just like bouncing back. These are at normal, these are normal to the plane of reflection, so they just bounce back and come back, right? And then from the ray diagram, it's clear that this is also like this A point is also just mapped to its to the negative y coordinate of this, right? So once again, v and u both are negative, so it's going to be inverted. That's why it's down, and v and u are equal. So that's another important thing. How do we do that? Well, of course, you got the mirror formula: 1 upon v plus 1 upon u is equal to 1 upon f, which I like to write as 2 upon r, because right. Uh, and then if your u is negative 1 upon r, just get 1 upon v is equal to 2 upon r. Oh, sorry, in this case, in this particular case, your r is negative, right? So instead of actually going for the complete sign convention, I'm just gonna say r is the positive radius, right? So not the sign radius. In that case, this will be like minus 2 upon r. I know, just to simplify stuff, right? If I yeah, I should have done this in the correct way. R should have been negative, and then, but whatever. And then u is of course just what's like negative r, right? So this is going to be plus 1 upon r, and this is equal to, of course, it's negative 1 upon r. So v is also just negative r. There we go. That proves that it's going to form at central curvature once again, right? And this only happens for paraxial rays and stuff. What if this is not? I don't care about that. Do we really care about that case? No, we don't. Oh, and by the way, like I just forgot to mention that spherical mirrors like these only work good when we have paraxial rays, but parabolic mirrors, they have a true focus, right? So, or like I don't know, elliptical mirrors are not good. That will only work when the object is at focus itself. So parabolic mirrors, right? Those actually work because they will have a true focus. So using those is like much better. Why not, right? Okay, beyond C and F. So right, so our u is now smaller than negative r, right? So u is smaller than negative r, or you can say like negative u is bigger than r. So negative u is a positive quantity, right? So you can just take the reciprocal, and it will be like negative 1 upon u is bigger than sorry, it should be r, not 1 upon, and it should be like bigger than 1 upon r, right? So yeah. Now we know 1 upon v is just equal to in this case like negative 2 upon r. No, yes, yes, no sign convention followed. Okay, understand that. And then minus 1 upon u. So right, and this thing just becomes like bigger than minus 1 upon r. So of course it's like 1 upon negative v is bigger than 1 upon r, because we kind of, I mean, we can already guess that V is going to be negative, right? Yeah. Uh-huh. Because right, right. So from here, you can just say, okay, negative V is like less than R, so V must be bigger than negative R. Oops, I think I messed up somewhere. Negative V is less than R, so yeah, actually that is correct. So V is bigger than negative R. That does mean that its magnitude is less than R, which is what this equation says. So that's why it's between C and F, and of course it's not at infinity, so it's not gonna go to the focus right away. So it's somewhere between C and F. So it's the opposite of what happened it over here. So when the object was beyond C, your image was between C and F, and now when it's oh wait, I solved for that, so it should have been for it. But then whatever, like 1 upon D plus 1 upon U, so it's all symmetric, right? You don't have to worry about that, right? So for lenses, it's not symmetric, but then for mirrors, I mean, yeah, it's just symmetric, so bonus. Yeah, so that means this can be carried over here by retracability of light and everything. So yeah, it works at F. So whenever object is at F, of course going to be at infinity. Oh, and by the way, your angle made over here, so angle at the pole or whatever, right, that angle is actually carried over. So you got this mirror, you have this object at focal point, this angle is just carried like that, so it's the same thing, of course, because like reflection at this surface. Yeah, and what that means is like an object is going to be infinitely large because it's at infinity, x is equal to infinity, sorry, negative infinity. So your right, image height will also be very large. They are saying highly large, but if it's actually at true infinity, it's going to be infinity as well, right? Size is also going to be infinity. But of course, I mean, true infinity is never practical. It's just a really far away distance. That's what you're saying, okay? Real and inverted, of course, we can see it's inverted, and then it's real because yes, all these three are actually going over there, right? Between P and F, so then it starts becoming virtual. Between P and F, this becomes enlarged, virtual, and erect, right? So, thing is, when it was at focus, these diverging rays, this mirror could converge it enough such that these would now become parallel. But now when it's at a distance smaller than focus, these are so much more diverging that it cannot even, it just cannot make them parallel. It will have them being diverging now, right? And of course, they are less diverging than what they initially were, and that's why you have a bigger distance, right? But they still are diverging. So it's going to be a virtual image, right? It will appear as if they are coming from a point, although they are not actually going from a point, right? Yes. So this is nice. Yeah, whatever. I'm not gonna read that. Okay. What is this? What is this diagram? Oh, so this fine. Ray diagrams. Yeah, I know how to do it. I have done it in school, at least. Yeah, I don't wanna do that ever again because now I feel that these are not the best way to teach optics. Instead, because like what it actually happens is that in these diagrams we exaggerate every single angle, every single distance, which is not correct. What should happen is that you should treat it more mathematically, right? Follow proper sign convention, not just talk about it geometrically. That should what should be happening. And that's why I derived all of my equations using just coordinate geometry, nothing else, right? So no proper geometry, no special cases, and then combine them together. No, nothing like that. I just did that in a single stroke. Anyway, enough about that. Let's keep going. Oh, and by the way, for lenses, the problem is that your focal length will actually change when you go from so if you're going, say your rays are going like this, so your image, sorry, your object is, I don't know, somewhere over somewhere in the negative x direction, right? So this might be your lens. Then your rays are going like that. Then what will happen is that you take your focal length to be the positive version of what you generally take, right? So okay, I shouldn't say it like that. You take the focal length to be the normal normal focal length, right? So for convex mirrors could be positive, for concave, sorry, convex lens is going to be positive, concave lens is going to be negative, and whatever. But then when it's going opposite, so when your object is over here, right? And by the way, it's not a virtual object. So for a virtual object, the rays are still actually going in the positive x direction. But now for a real object, these are actually going in the negative x direction. That's why you have to take the focal length to be negative, because this focus is actually what's being used, right? And then I have another alternative reasoning for that. So that reasoning I was just that the refractive index becomes negative of what it should have been, right? Because now the rays are going backwards. But you should just go and see that whole you know derivation I did, and then it will start making more sense that why I'm talking about negative refractive indexes, right? Cartesians, right? So this is what they're saying, that along the positive x-axis, your incident light should always be along the positive axis. That is, you define your positive x-axis such that it's along the incident light all of the time, right? But now we know we don't need to do that, right? And the thing is, like, doing this has problems. You have to constantly flip your sign conventions all the time, and it just becomes so complicated to do that. Now, instead of that, if you just switch the focal length from positive to negative or something like that, that would be more convenient. They never taught me this. Why? I don't know. I don't know. Why did they tell me that this is also something you could do? So for mirrors, you don't have to worry because you cannot go the opposite way, right? That wouldn't make sense. Because this is not the silver surface, so right. But for lenses, you can go the opposite way. So you have to take the focal length negative in that case when you have a real object at that particular point. In effect, when you're or you have a virtual object in the negative x part, in that case as well, your rays are going in the negative x direction. So you have to take negative of the focal length. I mean the usual focal length, right? So that focal length is not, I mean, it's not magnitude, it's actually the sine focal length that we're talking about, negative of that sine focal length. Okay. Then you got mirror for the corner. No need for all of this geometry, really. Just look at that. Just right. And guess what? These people are going to give you so much of this kind of geometry and then extending it. Extending it to special cases, right? They are not deriving it for the special. Sorry, they are extending it to the general case. They are not deriving it for the general case. They are extending it, right? I don't like that. Right, but fine, it's also valid derivation. You can do it like this. And then actually it's more like two derivations together, because first you have to prove that the focal length is actually r upon 2. And then from that you can actually figure out the mirror formula. So yeah. Oh, okay, this time they're going the opposite way. They're first going the mirror formula and then from that, right. So that's the more, the easier way, right? So the way that I did in the school was that I first proved that the focal length is actually r upon 2, and then I proved the mirror formula, because of course this is much more complicated than just proving f is equal to r upon 2, right? Okay, but yeah, if you already have this, it's easy to see what the focal length is. Lateral magnification, just magnification. There's also, I think there's the other magnification, which is, yeah, we don't talk about it. Power of a mirror. So for power, for a lens, the power is n upon f, but for a mirror, it's defined to be negative 1 upon f, right? So yeah, it doesn't matter what refractive index surrounds the mirror, it's always going to be negative 1 upon f. I know it's inconsistent, right? Yeah, but whatever, fine. Oh yeah, these kind of questions. So you actually have to differentiate and then get the thing. I don't like that. So it's got this formula one plus u plus one. Sorry, one plus p plus one upon u is equal to one upon f. Why don't you just differentiate it right away, right? So this will give us like negative one upon v squared dv upon. I know v looks like it's the velocity. It's not the velocity. It's just uh, some better symbol for this. No, they don't have. But yeah, it is dv upon dt, and v and u are not velocities, right? And then negative 1 upon u squared du upon dt is equal to 0. And from here you can get the thing like dv upon dt, which is the velocity of the image upon du upon dt. That is equal to negative v squared upon u squared, which is like the negative of the lateral magnification squared. That works. Yes. Oh, and what about the y coordinate, you ask? Yeah. So we know that h upon h naught is equal to v upon u, right? Or yeah, basically. So now I just want to take the derivative. So h is just equal to v upon u times h naught. In other words, right? Whatever. And then you just need to take a derivative of this thing, so that you can get dh upon dt and then dh naught upon dt and all that. Yeah. So it's gonna be like dh upon dt is equal to, so you can first take the derivative of v upon u. So your magnification changing, which yes, it can happen. Oh god. Right. So what will that be? It will be like dv upon dt upon u, and then you got minus v du upon dt upon u squared, right? And that times h naught. And then remember the fact that h naught is actually very small, right? Okay, maybe that is up to the scale, so it might not even be that big, or I mean, it might not be that small, in fact. Anyway, and then you got plus v upon, which is the magnification, and then just dh naught upon dt. Yeah, so usually h naught is a fixed quantity, so you can just get rid of this whole thing. But what if it's not? What if it actually is having a variable xy coordinate, right? What if your object has a variable xy coordinate? Then you cannot get rid of this. Did they do this? Did they write the vertical velocity and stuff? I don't know. No, so they did write the body. Oh yeah, so the y coordinate. So velocity of image in the y coordinate is equal to magnification. No, that is really not correct, you know. That's not correct at all. I mean, where did this term go? You also need this term. Velocity of, no. That's not correct. You also need this term. You can't just do this. This is wrong. How did they? Or maybe like this actually cancels out to be zero. Let's see. Maybe that's what's going on. So dv upon dt, that's just equal to negative v squared upon u squared times du upon dt. So just putting that in there, what do you get? Du upon dt common, and then negative v squared upon, yeah, it doesn't look like it's going smoothly. Ah, what is this? It's just like negative v squared upon u cube, and this thing is just negative v upon u squared. Of course, these are not matching up. This is not good. Right. Well, this is like du upon dt, and then you got negative v upon u. So let's just take that common. So this will be like v upon u, yes, and then plus 1. So this is magnification plus 1 over there, and yeah. What is this? I think once you know what the velocities actually are, this will become easier to calculate. Anyway, so this is not correct. I mean, why would you just say that it's m times velocity in no, No, please, it's not right. What are you saying? Like h naught is equal to 0. Oh, so you are neglecting the whole term. Might make sense if actually it is negligible. But what if it's not? What if your dh upon dt is very, very small? So like dh naught upon dt is small, and then actually the other term really does matter. What if that happens? Then this formula just doesn't work, right? Okay. Okay, no, they do have the thing. Sorry. Uh, right. So they do have the thing. And so what, wait, why is this equal to the velocity? No, that's not necessary. Velocity of image in x direction is equal to negative the velocity of image in the y direction. Why? That's not necessary, is it? But it's correct that the velocity of the image in the y direction is like dm upon dt h naught plus, yeah, all that stuff, right? That at least is correct. Oh, and it's a mirror, and that's why you have this negative. I almost forgot that. Fine. Now that's understandable. So in check exercise 2, let's do it. Determine the okay, first question. Determine the image distance and the why did they put up the answers right away? Okay, image distance and image height for a 5 centimeter tall object placed 45 centimeter away from a concave mirror having focal length of 15 centimeter. Right. Image distance and image height. Just find v first of all. So got 1 upon v plus 1 upon u. So 45 centimeter away from a concave mirror is like equal to 1.45. That's equal to, so v is in centimeters. Focal length of 15 is negative 15 because it's a concave mirror. So it's going to be negative 1 upon 15. And you got 1 upon v is equal to 1 upon 45 minus 1 upon 15, which is like minus 3 upon 45. So this just becomes minus 2 upon 45. And that just means, okay, v is negative 45 upon 2. Well, u was negative, uh, what was it? Negative 45, right? Supposed to be 2, sorry. So, yeah, what happened is that this object shrink to half the height. So your height will now be just 7.5 centimeter, right? And it's going to be inverted, of course, because negative v upon u. So I'm going to say h is equal to, so I'm gonna put that negative because yes, so negative of 7.5 centimeters and v is equal to negative 45.2, which is negative 2.5 centimeter. There we go. This should do it. Yeah, this should do it. Okay, next question. An illuminated image is magnified by 2 when the object is placed at 22 centimeter in front of a concave mirror. Magnified by 2. Oh, so the negative v upon u thing is like 2. Okay, that just means v is equal to negative 2u, right? And they are saying object is placed 22 centimeter in front of a concave mirror. So u is just negative 22. That just means v has to be 44. Nice. Oh, that's perfect. Determine the image distance and the focal length of the mirror. So image distance is what? Why did you do that? So image distance is just a piece of cake now because it's 44. So yeah, that was easy. So v you know, and from here you can figure out focal length. So 1 upon f is equal to 1 upon v plus 1 upon u, which is like 1 upon 44 minus 1 upon 22, which is negative 1 upon 44. So focal length is just negative 44 centimeters, all in centimeters. Okay. Third is magnified inverted image is located at a distance of 32 centimeters from the concave mirror to focal length. Fine. Determine the object distance and tell whether the image is real or virtual. Magnified inverted image. So yeah, your magnification is just negative, but its magnitude is more than 1, right? So you have to tell whether the, and also you have to determine the object distance. Oh wait, why did you specify all of this? You just had to give us the distance and the focal length, right? So distance negative 32, right? So 1 upon v is equal to 1 upon f, which is negative 1 upon 12, and then you got minus 1 upon u. So it's going to be plus 1 upon 32. Yeah, which is, let's just say, take 1 upon 4 common, it's going to be negative 1 upon 3 plus 1 upon 8, which is negative 5 upon what? 24, right? 1/4 of negative 5. Is that correct? Yeah, that must be correct. So negative 5 upon 24, which is like, okay, 1/4 of that. So negative 5 upon 96. So our V is just negative 96 upon 5, right? So what is that? It's 19.2 centimeters. Let's look at that, 96 upon 5. That's equal to, so 1, and then you got 40. So you would just need 45, so 9, and then point, so 1. Yes, it's 19.2. So yes, wait, I mean, okay, why am I writing this down? They already gave us the answers. There's no need for us to do this thing, right? Oh, wait. The last question, they said that, wait, what? Oh, sorry. Okay, it's 5. Right. So these both questions I did incorrectly, huh? So it's a 5 centimeter tall. That's why half of that's going to be 2.5, not. Yeah. Okay, I messed that up. So it's supposed to be negative 2.5. Sorry. Or maybe just my 7 looks like it. This was 7.5, I think. So this should be 2.5. And of course, focal length is not this thing. You are saying focal length is 14.7. Well, you got V is equal to 44. And then U is just negative 1 upon 22. Okay. So when they said it's magnified by 2 and it's inverted, they actually mean the magnification is negative 2. And that means negative V upon U is equal to negative 2. So V upon U is equal to 2. And that means actually V is negative 44. So our focal length would just be 1 upon focal length would be negative 1 upon 22, negative 1 upon 44, which is negative 3 upon 44. So focal length would be 44 upon 3, right? Magnitude wise. So 44.3 is 14.7, I think. Uh, yes, looks correct. So okay, why am I writing these down? I don't get it. There's no need for writing this down. So right, right. So this was correct. So these three questions done. Focal length is located. So focal point is located 20 centimeters from the convex mirror. Object is, so f is basically plus 20, and object is placed 12 centimeters from the mirror, so it's negative 1 upon, right? Determine the, come on, okay, this was easy. So 1 upon v is equal to 1 upon f, which is just 1 upon 20, and then you got minus 1 upon u, which is like plus 1 upon 12 like this. Yeah, right. So this is going to be what? It's like 1/4 common, you got 1/5 plus 1 upon 3, which is going to be 8 upon 15. So 2 upon 15 is the way to go. So 7.5 centimeters. Makes sense. Right. This is understandable. In the figure shown, if the object O moves towards the plane mirror, then which direction will the image 1, which is formed after successive reflections from M1 and M2? What? Object O moves towards this plane mirror. Oh, so, right. In which direction will the image 1 be formed? Okay, move towards. Okay. Understandable. So, always moving like this. This guy's image when formed by M1 is moving in this direction, so it's somewhere over here. And from the looks of it, I think it's, yeah, it's at a point which is more than the center of curvature. Successive reflection from M1 and M2 respectively, right? So first M1 and then M2, or you want them? No, it must be first M1 and then M2, right? So you got an image over here, and then this will have its image as, so it's, I think, yeah, it is bigger than the radius, so it's going to form somewhere between, what was this, F and C? Yes, uh, right. And then this is going towards C, so this also is going towards C, and that means this is actually going in the right direction. So yes, right. It's shown by multiple mirrors. Okay, nice. Oh, so your y coordinate can also change. Oh, I didn't ever think of this happening. So throughout my derivation, whenever I did, I only took the x coordinate with the thing that's changing for these mirrors. But now the y coordinate is fine. You can definitely do that. So you have this whatever refraction. Yeah, whatever. We already know this thing. Laws of refraction. Come on, that's everyone knows that. Derivation. This is not the correct derivation, you know. So they say that light taking the least time just makes this happen. No, no, no. It is from wave optics, right? So your wave fronts, those change their orientation, and that's why this happens, right? So if you have like wave front, so this is our one wave front, and then it's going in this medium. What happens there is that the speed actually decreases. So yeah, Huygens principle. That's what is going on. So this, I don't know, maybe it's like a crest or something. So first this will hit and then it will slow down. So now it's radiating whatever it's yeah, its electric field is like spreading like this, and then this hits it after some time. So now it spreads like this. So once it has spread to a big distance, this is spreading to a smaller distance, and then this hits it, and then that's spreading to a smaller distance and everything. And yeah, so right, you can see your wavefront actually doesn't go the same way, right? It's going in this kind of direction because your speed is different. If your speed was the same, well, yeah, then this would keep on going in the same direction. How do I even should I even derive that completely? No, there's no need for doing that. It's the ray optics, not wave optics. But yeah, right, if you actually want a good derivation for this thing, search that, right? Search the wave optics explanation of why this happens. This is, yeah, this is, I mean, okay, it's a good principle that it takes the least path, but really that's not what's causing this. And then the critical angle or whatever. What is this? Pinhole, top of the thin rod, this height edge. Okay. Uh, okay, what is this illustration? An observer can see through a pinhole at the top end of a thin rod. Top end of a what thin rod are you? Is this a thin rod? I think so. The beaker height is 3h. So this is a beaker. When the beaker is filled with liquid up to height 2h. What? What do you mean by that? Oh, so this is the rod. Sorry, this is the rod. And okay, so it really is filled. It has a height 3. Okay, this is weird. So this must be filled over here, right? But why is this 2h? Huh? Sorry. Uh, Now, why is this 2h? I don't get it. Because height is 3h, radius is h. Oh, so that's why this, okay, this is the diameter for that. Oh, and the height is actually 2h, right? Okay. He can see the lower end of the rod. Ah, right, because it's refracting. Usually he wouldn't. What is the refractive index? Fine, fine, fine. That's right. It's not such a bad question. I think it's good enough. Whatever, whatever. We are not doing this. We'll go to the exercises. In chapter exercise 3. What's this? What's this symbol? A ray of light is traveling through air towards a lucite block in the shape of a 30-60-90 triangle. Trace the path of the light ray through the lucite block shown in the figure. So, oh, just it hits like that. Right, right, right. So first there will be no refraction because incidence angle is 0, and then it goes over here. So now it's in the refractive index of what? 1.4, and yeah, it's hitting it at whatever this angle is. Well, from geometry, it's only 30 degrees. Just prove that. So it's hitting normal to this surface. This angle has to be 90 degrees, but then this angle is just 30 degrees, right? So this means this is supposed to be 60 degrees, but then this is the other normal. So this must be 30 degrees because this was 60 degrees. So then we our incidence angle is now 30 degrees for this surface. So what will your refracted angle be? Refraction angle. So sine of 30 upon sine of r is equal to 1. It's like 1 upon 1.4, I think. Yeah. And from that you get the angle, but I won't do it because 1.4 really. What is still sine of 30 is just 1 upon 2 and then upon sine. Or you could do the opposite ways like sine r upon sine I is equal to in this case it's gonna be like just use theta maybe. Yeah, theta upon sine 30. This angle is theta, and that's equal to this reflection of this thing as seen by this guy, which is of course 1.4. So this is going to be 1 upon 2 of this guy, which is 0 0.7. So 0 0.7 upon 10. What has sine theta being 7 upon 10? No idea, right? Just move on. According to them, it's like 44 degrees. Why? I don't know. Oh, because like square root 2 upon 2, right? So square root 2 is 1.414 something, and then upon 2 is like 0.70 something, right? So it's close to 45 degrees because of that. Now they are saying it's 44 degrees. We don't know how to do that. Actually, we do know. It's like Taylor series. Yeah, just whatever. I'm gonna make a Taylor series for sine of, or you could just use small angle approximation. Yeah, because for cosine the expert we can neglect that. So yes, it's actually doable, but I won't do it. Refraction and no, I'm not talking about the Taylor series for sine inverse of some big angle. No, what I'm saying is that just stupid. 7 upon 10 is equal to sine of 45 degrees, which is like 5 upon 4, and that minus of x because clearly it's less than that. So what will this x be? That's what you're looking for. So you can write this thing like 1 upon square root 2 sine a cosine x, and then minus 1 upon square root 2 sine x. But then x must be small because it's so close. So you can just say it's like 1 upon square root 2, and then cosine x is approximately 1, right? So minus x upon square root 2. First degree approximation. So from that, just get 1 minus x is equal to 7 upon 10 times square root 2. And from there, x is equal to, right? So you get the idea, right? X is just equal to 1 minus 7 upon 10 times square root 2. This is in radians, so you will have to convert that to degree. And then in doing so, maybe this just becomes that, right? It might just become a degree, 1 degree, whatever. So multiple phase boundaries. Oh yeah, so I think it's better if I just write down a differential equation for this kind of thing happening. So I remember, oh whatever, right? I was thinking of something completely different. That was whatever, right? So what's our aim? Refractive, yeah. So a differential equation for this kind of thing happen. Oh wait, it's all discrete, right? Because these are like, yeah, the refractivity is constant throughout this lab and whatnot. Oh, huh. That was unexpected. But yeah, I'm still gonna do it. Still, what happens if your slabs are not of the uh, of like finite thicknesses? They're just really small, and then your effectiveness is changing not by a lot. So right, what do we do? Your angle doesn't change. So angle of incidence when going from this point, sorry, yeah, this angle that it makes vertical, it doesn't change when you're going from this point just below this index, so just below this interface to this point just above this, right? And that's important, right? That's very important. Sometimes it could change. It could change if actually you have not parallel surfaces. Yeah, so slightly deviating from that, right? Now because it doesn't change, what do we do? Uh, so throughout its motion, if this is like going through a bunch of slabs, this is how the light's path is. If it's making, say, theta angle at any point with our normal, what do you have? Just have n as a function of this x distance that it covered. So, right, and then you just have n sine theta is equal to n naught. So at x equal to 0 times sine of whatever angle it came in with, alpha. That's one equation for this. And uh, yeah, like this, why you don't even need a differential equation, do you? Well, yeah, what? This is not what we're looking for. Should I just differentiate this thing with respect to x to get the, no, why? This is a much better condition than that, right? So no need for doing that, I guess. Oh, what if you're n not n sine? So yeah, if you don't know your n not n sine alpha, then you could definitely differentiate this thing, right? Oh yeah. But hey, that's just unnecessary. Huh, so this even works for non-discrete. Nah, whatever. Engine exercise 4. A concave mirror is placed on a horizontal table with its axis directed vertically upward. Concave mirror, horizontal table directed upwards. So this is our table. I'm drawing it like that. It's supposed to be horizontal, but whatever. And then you got this concave mirror, something like a bowl or whatever. Um, yes, so this is its axis, whatever. Let O be the pole of the mirror. This is point O. Then C is the center of curvature. C somewhere over here, I think. Over here. A point is placed at C. Okay. It has a real image also located at C, of course. A condition called auto called whatever. So if the mirror is now filled with water, so you are filling this with water, right? The image, so refract. Wait, you didn't give me the refractive index of water. Hey, how am I supposed to solve this? Oh, so you just have to do this. Oh, then fine. Just assume water has a refractive index something, so something bigger than one, of course. It has a mu refractive index. Then let's do the thing. Of course, you know what this is. It's just gonna be yeah. So your u is just well, let's just say it's r. So to stick with the sign convention, right? Or maybe not. Maybe just don't do that. It's gonna be negative r, where we take r to be the positive uh, quantity. So this will have radius of curvature negative. I know it looks weird, but yes, it's gonna be negative r. That is, this point's coordinates are really just negative r comma 0. That's what you're seeing, right? Okay, so now let's do it. Of course, the final refractive index will just be negative, so negative 1, sorry, because it's in the air now once again. And upon the position of the object, which is v, sorry, of the image, and then minus, so the initial refractive index, which is going to be 1, and that upon the position of that, so it's going to be 1 upon r, right? This minus 1 is positive, and that's equal to, so for the first surface of your r is just 0, and huh, that's nice, it cancels up, it cancels away really. And then for the next surface, uh, so your refractive index is going from mu to negative mu. So it's going to be like plus 2 mu. Oh, sorry. Final minus initial, right? All of the time. Final minus initial. So it's going to be like, okay, whatever. Plus minus 2 mu. And that upon the signed R value. In this case, it's going to be like negative R plus. Here R is this unsigned value. Right. So there we go. Negative 1 upon V plus 1 upon R is equal to 2 mu upon R. So 1 upon V, or I just go with negative 1 upon V because we kind of know V is going to be in the negative direction. Yes, and that's going to be equal to, let's just see, R, and then you got 2 mu minus 1. Right. So, huh. So R upon mu minus 1 is the distance from the O for the image, right? Now, what might that be? What is mu for what? I think it was like 4/3. No, that was for glass. Oh no, I don't remember what the refractive index of glass and water was. Is that real? Okay, this is just. Uh oh, This is not good. How could I forget that? Uh, okay, I think water was 4/3 and glass was 3 upon 2. Is it so? I don't know. Both cases, it's something bigger than 1. So this is like, okay, mu plus mu minus 1. Mu minus 1 is just some kind of positive quantity. And then mu is, of course, something bigger than 1. So as a total thing is going to be bigger than 1. So something bigger than 1 upon r. And that just means v is something that's less than r, right? So that's why it's between c and 0. Understandable, right? And you might be thinking, what did I do over here? What was this? Just go and read that whole note I made, and then you will see what I did is just that I applied the concept of negative refractive index. I know it's weird. Why would I want to use this? But it works, right? Look at this. It was so easy. And yeah, otherwise I would have to actually analyze each refraction or reflection, and that would be so much not good. That's it. Next question. And yeah, we'll see how correct actually is to just do it like that, because we'll get some questions that this might not work, and we'll see what went wrong. Okay, so this is it. It's just this much is integral x 4. Are you serious? Okay, refraction through rectangular glass slab. Oh yeah, so lateral shift. Right. So it's um the tan of this angle, this diffractive angle, and that times the thickness of this. That's what this shift is. But what we are looking for is this shift, right? So what will that shift be? So yeah, this thing, right? It's gonna be this thing, and then you got 90 minus r over here. Wait, it's not right. It's gonna be I minus r. I minus r over here. This is going to be sine of that thing. So sine of I minus r. And then you got this already was just something like, yeah, this whole thickness upon cosine of r. And then this times the thickness, of course. That should do it. Oh yeah, that's exactly what they got, huh? So that's our lateral shift, which is, yeah, it's an easy derivation. Okay, understandable. Particular cases when I is approaching 0, normal incidence. What is this? Oh, so it's a graph between angle of incidence and lateral shift. So when I approaches 0, in that case r also approaches 0. So then this kind of just becomes I minus r upon, cosine r becomes 1. Yes, approximately 1. And then this times t, right? But we know that sine I upon sine r must be, oh, so you're saying like, okay, delta is equal to t itself. That's unexpected. Oh, okay, no, that's for a different case. For this case, this is happening. So, right, of course, we know like sine I upon sine r is equal to n, and that just means that r is equal to I upon n, right? So I upon mu, whatever. And that just means it's like I times 1 minus 1 upon mu times t. That's what this shift is. Right, understandable. And then you have this other case where I approaches pi upon 2. Oh, right. So then it's gonna go to the critical angle. So you are saying, oh, of course. So if I is pi upon 2, this whole thing just becomes sine of pi by 2 minus r, which is just cosine of. Oh yeah, that was so easy. Like this whole thing becomes t, right? And we know r is going to be the critical angle or whatever it might be. Yes, understandable. Oh yeah, this thing. So too bad I already know how to do it. So what was the thing? Like mu2 upon v minus mu1 upon n2 n1 upon u is equal to uh right, that's equal to just 0 because radius or curvature is like 0, and from here you just get that. Wow, it's like v upon mu2 is equal to, it's not supposed to be negative, it's supposed to be just u upon mu1. In other words, your v is going to be mu2 upon mu1 times u, right? And your shift. So your shift will be, oh, and okay, the shift happens when you actually go through a whole slab, right? Hey, what was that formula? Oh god, I just don't remember that formula now. What was that formula? It's different depending on thickness. It's like the shift is. I don't think that was necessary. Hey, this is like for every single refraction, right? And then you could just think like v minus of xi upon mu I. So I should not say v. I should say, I think. Yeah, actually, no, this was quite complicated to derive that full thing, right? So that's not, it's not gonna work. It's not worth to do that. Uh, right. So for the case when it goes from some medium and comes out with the same medium, right? What happens is like the shift, which is our delta x thing, just like just you know final image minus initial, something like that, right? Yeah, so the distance between the final image and the initial sign distance, yes, that was just equal to summation. So from so if there are like, I don't know, how many mediums do you want? Let's say there are n mediums, no, k mediums, right? Yeah, so not including the last medium, right? It will be k mediums. It's like 1 to k, and then each of them was like, okay, you got some thickness, so ti, so I equal to 1 2. So first, and then just got 1 minus 1 upon the mu I think, where mu I is just like the refractive index of this slab it's going through upon the original index it was in, right? Yeah, that's understandable. It's really understandable, I think. Yeah, right. Isn't that correct though? It should be, I think. So, yeah, like for the first slab, which is right. So for the first index thing, it actually does not produce any shift because right mu I just becomes a one. This goes away, right? So you don't actually have to even worry about that. Oh, and what does that actually mean? It just means that uh, oh, this is like what? It's gonna be like di 1 upon n and k. Yeah, that was the thing. Minus 1 upon and I sorry, summation of this thing, right? Yes. That was the optical shift. So the optical distance happened, yes, something like that, right? Now but you're dividing by the index, so you should actually multiply by the index to get the thing done, right? And over here what you just did is like you multiplied by nk, right? We know it's actually going to be like v upon nk minus u upon nk, that is this thing, sorry, v upon n naught, that is this thing. That was the actual formula. So the shift formula. I don't know. I just remember this thing, and I thought maybe I don't remember it. So now I do. So near normal view, right? This we can just deal with it on time, right? You don't need to memorize this. Uh-huh. So it's whatever. Just keep on moving. Yeah, whatever. Inch says fine. A person looking through a telescope just sees a point on the rim of the bottom. So they've given us a diagram of a cylindrical vessel when the vessel is empty. Straight is sorry, interruption. Fine. A person looking through a telescope just sees a point on the rim of the bottom of cylindrical vessel when the vessel is empty. Uh, it's not looking normally. It should be right above it. What's this guy doing? When a vessel is completely filled with liquid, he observes a mark at the center of the vessel. Oh, okay, okay. He's not looking normally uh, with respect to the surface of the liquid, but he is looking normally with respect to this lateral surface thing. So yes, actually what's happening is like you got a block of water over here, and then the telescope is actually something. So yeah, just imagine it's actually a very flat container. Just have a block of water like this, and then this guy is looking very much like this, right? This is our telescope, and this is like this guy's eyes, and this is what he's looking at. Yes, 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 yes. So just have this, have like whatever this thing is. It's a big block of water. Yes, yeah. So it's almost as if you have this situation. So if this is, I don't know, diameter d, then this guy is like d above it. So there's a layer of d, right? And then this is above it, and it's looking like it. Right, understandable. This is our eye. Yeah, so this is what it originally was, and now where will its image be? That's what we are looking for, right? So now he sees it at the center of the vessel. That means okay, it's got to be over here. So at d upon 2. Yeah, so the shift produced is just d upon 2. That's what we will say. And then you know how to figure out the shift. It's just going to be like the thickness, which is in this case d, and then you got 1 minus 1 upon mu. So mu for water is right. The n naught and nk thing is just there's no nk actually. Oh, n naught is somehow okay. This is not good. Uh-oh. N naught was hey, you know what? Scrap that. What we'll do is we'll say, okay, this I'll just put a small layer of air over here so that this is now doable. Right. This will be good now. Isn't that right? Yes, 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 yes. This should work. This should, right? Yes. Yes. So now the shift will just be this thickness is just d, and then you got 1 minus 1 upon mu. So n dot and n k are now the same, and that's why this will work. So mu is just they gave us what mu is 1.5, so it's going to be 2/3 over here. Yes, so the shift produced is supposed to be just d upon 3, but it's actually d upon 2. That's not correct. Uh, wait, what? No, that is not right. It's not supposed to be d upon 2. It's supposed to be d upon 3, and this is clearly d upon 2. It went up with that much. This is not making sense. Why would that happen? Serves a mark at the center of the vessel. Wait, but this is not making sense. Wait, what? What is the height of the vessel if the diameter of its cross section? Wait, what? Height of the vessel? How is that relevant to this question? Rim at the bottom of the cylindrical vessel, and the vessel is empty. The vessel is completely filled with liquid. This is not, it's not good. He clearly is looking like this. This is a parallel to the surface, not perpendicular to it, right? This is not making sense. But according to him, what's happening is like, okay, these rays, they appear to be such that it's coming from here. So he thinks the rays are like, so it's not, you don't have to apply this formula. Instead, you just have to think that, okay, there's like a bunch of rays going like that, this is what he sees. But now when you fill it with liquid, what's happening is that these rays deviate, and now yeah, this is what happens, huh? Oh, sorry, this is not apparent depth, it's this thing, it's lateral shift. That's why you are doing it like that. Oh, sorry. This is so stupid of me to do, right? Yeah, what was the shift thing once again? Just got this. So in this particular case, you just have this ray of light, and then usually it would just go like that. But now, this guy thinks that it's coming from here, from this point, but we clearly know that the rays, they will just, right, it's like aimed for that. Oh no, these are not. These are not. They are definitely right. It's gonna bend away from the normal. So when this particle will bend, you got this ray, it's gonna bend like this, huh? But if it bends away, it will. This guy will think actually coming from here, which doesn't make any sense. So that's not what's happening, right? That's definitely not what's happening. What is happening then? It's not this ray that we're talking about, right? That's not thing. Oh, and of course, like, okay, just draw a better diagram. This is our eye. That's where it has to go. We got this, right? Now, without water, it just goes like this. But with water, according to this guy, what's happening is like it's thinking the mark is over here, so he must think that the rays are coming from here. But then, how can that happen? Well, clearly, you just have the rays refracting. That's why this should happen. And then going from there to there. Okay, this doesn't make any sense. The incidence is higher over here, and now it's lower. So how this angle decrease when it's supposed to actually go to a rarer medium? That's not correct. Yeah, this just cannot happen. Mu is equal to 1.5, which is not distinct from this. But then we know shouldn't happen actually. Now I just don't know what's going on. How would you do this? Because clearly it's going from denser to rarer. Then what should happen is like this should go away from the normal, and that's why. Yeah, but this is not the case over here. Center of the vessel. Center does mean this thing, right? So at the bottom. Oh, okay. So center means like center of mass, something like that. Huh? Huh? I think, right? But then isn't this like? No, it's not correct. It's going from this end to that end, and this angle is the same. So uh, right, it must be that this image is being found over here, right? Oh, come on. Something's not correct about this, isn't it? But this is not, he's not looking at it normally. How does this even make sense? Right? This is the point where it's looking at. Okay, just leave this question. Maybe this question is actually maybe it was not well written, and that's why it's like this. Ah, okay, whatever. Then you got prisms, an angle of right. So I wrote all of this in my note. Right, this thing I just didn't think much about it because I've never seen this before, and I've never seen it in questions as well. at least in all of the tests that I gave till now. So, is this even important? Why are they teaching us this? I don't know. Then you got reflection through a spherical surface, which is, yeah, I mean, this is the base that I built up everything on. Lateral magnification. Oh yeah, so this formula, I even derived this thing. Okay, lenses. Okay. Oh yeah. Once again, these kind of conditions. You know what? No, I just won't do that. Right? I know that one at least. But once again, this question, what was I supposed to do over here? The image is being formed like that. Uh, and clearly the rays are not going normal to this thing. So you cannot just apply a formula and get it done. There must be something else. And okay, if this was a very thin cylinder, it would have made perfect sense. Like, okay, this is what's happening. But it's not. It's not. I mean, in the diagram at least, it was not a thin cylinder. So that's not what's happening. It's only one formula that we know that we can use to actually figure out what happens for flat surfaces. But this is not a flat surface. Here it is at some angle. So from our axis, right? That makes it so much worse. This guy was looking normally, it would have been all correct, but now it's not. Maybe that question was actually dealing with this kind of, and then maybe they just drew the diagram incorrectly. What if we solved this by assuming it's like this and then it somehow verified itself? That would make perfect sense, right? Yeah. Let's actually go back to that and see if that is the way we should do it. Because there's only a few things we can do. Where it go? Oh wait, okay, I skipped that for. Oh, okay. Shouldn't have skipped that. Right, this thing. So let's actually assume it's like this thin cylinder. Alright? And now we can try to do it. So you know the height actually doesn't change, right? As you view, so it's our thin cylinder like this. You got this guy. This is the eye. This is what's happening. It's seeing over here, and then this is our surface of water that actually refracts and stuff. So we know that the height doesn't actually change, right? Yes, the height doesn't change. Our magnification is just one for this kind of shifting. So it should be somewhere over here. And does that mean what? Does that mean center of the vessel? Is that the center? No, it's not. So then, huh? What is it? We know it's gonna be like this. In case these rays are actually paraxial. Okay, anyway, and what's the shift? So if this is height h, this height is like h, and so this distance is still just r and r. Okay, now let's do it. What's the shift? It's gonna be h times of, and we know like the shift is just supposed to be h upon 2. The shift actually is just like h, and then you got 1 minus 1 upon mu, which is like 1 minus 2/3. So it's actually supposed to be h upon 3. Okay, once again, it's making no sense now. How could this be h upon 3 and be at the center? Unless the vessel is not right. That must be what's happening. But wait, it does say it's completely filled with a liquid. So it has to be just 2/3 over there, and it just gives h/3 as the shift. Diameter of. No, I don't know what to do over here. Just move on. Right, equation 6. A point source of light is placed at the bottom of a tank containing a liquid of refractive index mu. So a tank, a point source at the bottom of the tank. You got a liquid of mu refractive index. Level of the liquid is at a height h above the bottom of the tank. Okay. What's this? A bright circular spot is seen on the surface of the liquid when viewed from above. So on the surface, hence the point source of light. Of course, this is just mapped over here, right? Find the radius of the spot. Wait. Oh, it's not. Okay, okay, okay. It's not. That's understandable. That's understandable. Right. A bright circular spot, huh? Is it's not a point source anymore over here, right? So it's actually going. It's somewhere over here, and then it's emitting light, and that causes this. And right. No, actually, you don't even need to figure out what the image is and what's actually happening. All you just need to do is find the region in which it will let light escape, right? So this angle is theta critical now. And what's theta critical? It's going to be, of course, sine inverse of 1 upon mu, right? Okay, so now we know that. Let's call this theta actually. Right, so this is our radius of this bright spot. Yes, you just have r, and then you got this h. R upon h is equal to tan of theta, right? But you know that sine of theta is equal to 1 upon mu. So 1 mu is like square root of mu squared minus 1. Tan theta just becomes 1 upon square root of mu squared minus 1, right? And that just means, yeah, this should work, right? Uh-huh. This is also theta, and that's why this works. Okay, what fraction of the light escapes the liquid? Right. So, oh wait. What about the other part? So, what about the light it sent off in these kind of directions? So, does we count? Do we count that for the total amount of light or not? I don't know. What's the answer? Answer is this a comma or is it dot? Oh, first you want to find the radius, and that's gonna be h upon right. That's understandable because it's like r upon h is r actually. R upon h is equal to 1 upon square root of x minus 1. So r is going to be h times that. Okay, and then you have this is the fraction of light that escapes it. Uh, okay, half of 1 minus square root of 1 upon mu square. So this thing we know is just cosine theta. What we are saying is like 1 minus cosine theta, half of that is what escapes. Um, huh. Wow. Oh, maybe you're just finding like a solid angle that this actually is right, and then yeah, that's one way of thinking of it. Maybe that's what you're doing. So, what will the solid angle actually be? It's like just 2 pi into 1 minus cosine theta. Yeah, exactly. That's why they did this. So, in this case, theta is of course the half angle, and this is our solid angle. For example, when theta is pi, this just becomes 4 pi, which is the total solid angle of a whole sphere. And then this is the solid angle that actually has light escaping upon the solid angle. So the total solid angle, sorry, just 4 pi, so like half of 1 minus cosine theta. Exactly. That's what they did. So we do count this as this light, which actually got absorbed by this container. Well, that is also included in here. Nice. Right. Then you have this prism stuff, and where's the other exercise? This question. Where is the exercises? Then snap. Whatever. We know this. We already know this. It's just illustrations. Where's the exercise? Right, there it is. So, oh, you have two combined now. Huh. Okay, whatever. So, interpret says, 8. Hey, didn't we actually do this? Yeah, I think we did. Whatever. Fine. So first you have an inverted image is magnified twofold when the object is placed 22 centimeters in front of a double convex lens. So you mean like what's a double convex lens? What's the I do like weakly convex. Wait, is it actually two convex lenses combined or hmm. But we don't really care, it's just a lens, right? It's just a lens. That's what it is. It's some kind of something. Yeah. We can make it effectively just a lens. Right. Determine the image distance and the focal length of the lens if the image is real or virtual. So inverted image is magnified twofold. So magnification is um, negative 2, I should say. So V upon U is not negative V upon U, it's actually V upon U. V upon U is negative 2 and object is so sorry, yeah, like U is just negative 22. So V is going to be 44. So first part done. And then you want to figure out the focal length. So we know like 1 minus V minus 1 upon U is equal to 1 upon F. So 1 upon F is equal to 1 upon V, which is just 1 upon 44 minus 1 upon U. So U is negative 22, so 1 upon 22. This will be just 3 upon 44. So F is just 44 upon 3, which is turns out to be 14.7, whatever. Is the image real or virtual? Well, the image did form to the right, and that just means, yeah, it is real. So yes. A magnified inverted image is located at a distance of 32 centimeters from the double convex lens with a focal length something. Determine the object distance and tell whether the image is real or virtual. Oh, it's the same. Oh, so I think double convex is just a normal convex lens, right? That's what it means, I think. Or maybe it's an equiconvex lens. Does it really matter? It's just a convex lens, right? A magnified inverted image, so once again, M is negative. So that means it's a real image located at a distance of 30 centimeters from the double convex lens with a focal length of 12 centimeters. So your V is positive 32, I think. Object distance and right, right, understandable. So your V is positive 32, your F is positive 1 upon 12. So you just have 1 upon U is equal to 1 upon V minus 1 upon F, which is just 1 upon 32 minus 1 upon F is just positive 12, right? So it's going to be what? Just take 4 commas like 1 upon 8 minus 1 upon 3. So, hey, I've seen this. Minus 5 upon 24 times 4, which is minus 5 upon 96. So, U is just 96 upon 5, but in negative. So, it's going to be like negative 19.2. Yes, that's correct. So, yeah, it is 19.2 is real. From the magnification itself, we can say it's real. The focal point is located 20 centimeters from a double concave lens. Once again, what do they mean by double? I think they mean something like this. It is concave on two sides or something like that. Anyway, focal point is located 20 centimeters from it. Yeah, so F is just negative 20, I think. An object is placed 20 centimeters from the lens. Okay, so U is negative 12. Remind me, fine, fine, fine. 1 upon V is just equal to 1 upon U plus 1 upon F, which is negative 1 upon 12 plus 1 upon F, like negative 1 upon 20, which is, yeah, right, just 5, so like negative 5 upon 60, and then you got minus 3 upon 60, which is going to be negative 8 upon 60, which is negative 2 upon 15, I guess. So 15 upon 2 is 7.5, but then negative, and that's why negative 7.5. I think now I'm catching speed. 2 points of this P and Q are 25 centimeters apart. Where should a convex lens or focal length 90 centimeters be placed in between them so that the images of both sources are formed at the same place? Between them, you say. So 25 centimeters, 24 centimeters apart, and you want to place convex lens between them. The image is formed at the same place. Well, okay, that just like means 1 upon V is equal to 1 upon V plus 1 upon F. Yes, it must be the same. Wait, but if it's between them, that just means, oh no. So for the first guy, 1 upon v is equal to 1 upon u plus 1 upon f. Good. For the second guy, 1 upon v is equal to 1 upon u minus 1 upon f, because focal length should be negative of what we usually take. Right? Yeah, and then u is of course like, yeah, that's understandable. And uh right, what is the thing? Just call it like v, so u1 and u2 or whatever. So u2 is the one to the right. Okay, so you just have u2 minus u1 is equal to um what was the distance? 24 centimeter, right? And now into focal length is, wow, so you know that as well. So we don't really care what this image is, right? These two should be equal. And yes, that just means 1 upon u1 minus 1 upon u2 is equal to negative 2 upon f, and f is of course 9 centimeters, so it's negative 2.9. Now this is like u2 minus u1, which is 24 upon u1 u2 is equal to negative 2.9. So u1 u2 is equal to negative 12 times 9, right? So subtraction is just 24. Let's just say negative u1 is like u1 dash or something, right? So that yeah, so u2 plus u1 dash is equal to 24. And then what am I doing? Why am I doing this? I don't know. Just put that in there. Yes, like u1 plus 24, just put that in there and see what you get. It's like u1 squared plus, so 24, and then you got u1 once again, so it's 24 u1 plus 12 times 9 is equal to 0. It should be negative. Why is this? Oh, it is going to be negative because, yes. So 12 and 9, that doesn't give us 24. This is a definite multiple of 3, so you would need 3 and 3. Think 24, and it's also a multiple of 4, so you would actually like 2 times something. Yeah, so just say 6 and 6 over there, and then it's gonna be like, okay, you got that. Now you can break it as 6 into 6 into 3, right? So one of them must have a 3. So yeah, 18 and 24, that's how you're gonna break this. So u1 plus 18, and then u1 plus, sorry, 18 and 6. So 18 times 6 is equal to 25, 24, because, right, this means it's either negative 6 or it's negative 18. Both. Okay, what does v give us if that's the right? u2, what will that be? It's going to be 24 plus u1. So in case it's negative 18, u2 will be 24 plus 18, which is 6. Okay, so u1 is equal to negative 18 and negative 6. U2 will in that case be 24 minus 18, which is 6, and then this will be just 18. So it's in 18 is to 6 ratio. So yeah, that's how you want this to be separated, right? 18 centimeter from P. Does it really matter from which you place it from Q as well? If you just place it at 18 centimeter from Q, it will be the same thing, except it will be inverted. So instead of having the image where it should, yeah, it's gonna be opposite of that, right? All of it just mirror image, right? So no, this is just partially correct. You would also need the other case where it's 18 centimeter from Q. Okay, that's understandable. Next, if a concave lens is placed in path of a converging ray, real image will be produced if the distance pole, distance of the pole from the point of convergence of the incident ray lies between. Concave lens placed in path of converging rays. So you have a virtual object. That's what you're saying. Okay, a real image will be produced. Real, wait. Oh, okay, understandable. Right. If the distance of the pole from the point of convergence of incident rays. So, right. So what's U basically? Oh, come on. This is our concave lens. You got this virtual object which is at distance u from the right. Signed distance is also the same thing as unsigned distance in this case. And then you have some v somewhere over here. What you want is when will it form a real image, right? So like this will go to infinity when u is the focus, right? So if it's between the pole and the focus, you're done, right? It's gonna form a real image. If it's further than that, then it's so much already diverged that diverging it even more will just give us a virtual object, right? So it will, sorry, virtual image, because it will be like this, and then yeah. So between O and F, which is of course something between, yes, like its distance, this U thing will be between 0 and F. Yeah, that's what I said. Okay, next, in chapter exercise 9. Oh, what's this? Although the lens maker's formula is a very practical tool, the student must bear in the mind the limitations of the application. The simple formula and lens formula can only be applied when the lens is very thin. Yeah, that's like for it's granted for every single thing we are doing, you know. Yeah. Refractive indices of the media on either side of, yeah, you can modify this, of course. If the conditions are, come on, okay. Let's move on. Water refractive index for, right, it's refractive index 4 upon 3 for water, and it's gonna be 3 upon 2 for glass, right? Now it's understandable. Okay, water is in a tank 80 centimeter deep. Sorry, 80 centimeter deep. What I was saying today. Oil of refractive index 7 upon 4 lies on water, making a convex surface of radius of curvature r. Okay. Consider oil to act as a thin lens. Okay. An object S is placed 24 centimeter from the water surface. So this is our object. The location of the image is at X centimeter above the bottom of the tank. Find X. Oh, okay. All it's really, I mean, okay, just like two successive diffractions, that's all it is. Alright. And you are, of course, seeing from the from inside of this thing, I think. Yes, so from inside of this you are seeing understandable. Fine, let's do it. But okay, although like I'm kind of curious, doesn't your eye's lens also have a fixed refractive index? So if you are viewing it from here, but we do see it to be right, we do see the effects of seeing things from inside the water and outside the water, right? Um, yeah, in the end, it just rays at the top, right? So first it will, okay, this is kind of weird because if your eye lens is now having this other surface of water, oh, it's complicated. No, wherever your image is formed inside of this water as seen by some, you know, hypothetical being which doesn't need an eye inside of this water, right? It just senses wherever the intersection point is, right? If that you know it, and then you try to see it with eye, it will see it at that point because your eye's focal length can change. It will change such that this is actually correctly perceived, right? That's what should happen. Right. Now let's do it. So let's do it. So it's pretty easy. It's gonna be like, so this is our positive axis is going down. Yeah. In this case, your red which is like positive. So positive 6 centimeter or whatever. Final index is 4/3. So just use mu. Nah, 4/3. 4/3 upon V minus. So initial index is just 1. 1 upon this distance is what? 24 centimeter above the water surface is negative 24. That's what I'm saying. Yes, it's gonna be plus 1 upon 24 in that case. That's equal to, so right, for this surface you will have something. For this surface you want to not have anything. For this surface you got r being positive, and then what is mu 2 minus mu 1? It's like 7/4 minus 1, I think, which is just 3/4. So 3/4 upon r. That should do it. So yeah, uh, wow, that's correct, right? It should be. So like 1 upon v plus, so just divide by 4/3, that's like multiplying by 3/4. So this will be 1 upon 8 times 4, so like 1 upon 32 is equal to, just you multiply by, sorry, divide by 4, 9 upon 16 r. Now r is 6 centimeters, so it's gonna be 3 upon 32 over here. Thirty-two. So 1 upon v is just equal to 2 upon 30, 1 upon 16. So it should be 16 centimeters, right? From this, and then the tank is of how many, bottom of the tank, but what is this height of the tank? 18 centimeter depth. And then you are seeing it's 60 centimeter from this surface. So yeah, it's 2 centimeter away from the bottom, which is what they are telling us. Yes. Okay, once again, another advice from them. A lens is converging if the focal length is positive, diverging if the focal length is negative. The student should be very careful not to associate the terms convex and concave with the, yeah, so if your index is actually lower than air, then your concave lens becomes converging, which is, yeah, right. A concave, sorry, a convex lens can be diverging, and so this is not a, it's not an exercise. In fact, why this just, yeah, we don't need all this. Yeah, we don't need all this condition, right? Whatever. Okay. In chapter exercise 10, if a biconcave symmetric lens made of glass has refractive index 1.5, so biconcave, something like this. Okay, it has both surfaces of the same radius of curvature r. On immersion in a liquid of refractive index 1.25, it will behave as a something lens, converging, diverging, whatever. So just figure out the focal length. That's what we are saying really. So yeah, this is this refractive index is what, 1.25, and then this is also like 1.25, and this refractive index is 1.5. So the relative refractive index, like mu is just 1.5 upon 1.25, which is, so 0.3 upon 0.25, yes, which is like 30 upon 20. Yeah, that's right. 25 times 5, it's like 25 times 25 times 7. You get the idea, just divide by 5. And that's going to be like 6 upon 5. So mu is equal to 6 upon 5. Just do 6 upon 5 minus 1, which is just 1/5. And then that times 1 upon R1 minus 1 upon R2. Yes, minus 1 upon R2, not plus. Right. So both signed actually. So first guy has R1 being negative. Right. It's like minus 1 upon R. And both surfaces have the same radius. Nice. And the other guy is minus 1 upon R2, but R2 is positive, so minus 1 upon R once again. There we go. It's going to be like minus. Okay, usually what would happen is like, oh, wait. Oh, it's still just 1.25. It's still like mu is bigger than 1, right? So, yeah, that's why focal length is like negative, so it's going to be diverging. Right. So you send in parallel rays, it diverges it so that its focal length becomes negative. Right. You can see this is our 1 upon f value, that's negative. So yeah, focal length is negative. Often many problems ask for the focal length of a complex system consisting. Whenever I hear complex, I just go to like yeah, complex numbers and everything. No. And yeah, I just found out that there's also something called a complex refractive index, which to me doesn't make any sense. I just read some stuff about it. I just left it because yeah, it was out of my scope. Okay, so often problems may ask for the focal length of a complex system consisting of many lenses, mirrors, labs, etc. We will develop such methods and analyze a few of such problems, but in general, if in doubt, fall back to the basics. Focus of an optical system is that of the point where rays parallel to principal axis come from infinity and actually converge or appear to converge from. Okay, hence a general plan for such questions. Assume that objects at infinity. It's obvious. Yeah, calculate the final image. Sorry, final what image position under this assumption. Uh-huh. The position of the image is the location of the focus. What was this? Why are you telling me all of this? That's like the definition of the focus. Deviation produced by a thin lens. Del is equal to h upon f, where h is the height of the point where the incident ray. Oh, come on. Okay, okay. That's like this. Fine, fine, fine. So, for a thin lens, you say. So, yeah, this derivation is like, I can do this. I can definitely do it. Right? Yes, second way. So, in the end, it's like just hits on a part of a prism. That's what's happening. And you're saying it's h upon f. We'll see why that happens. So you got this kind of thing. You got, yeah. Now it's at the, so this guy has a radius of curvature r1. This has r2. Uh, yeah, right. So if it say hits at h away from here, so like this is where this almost parallel ray hits. Yes, it's taking this part to be something like a part of a prism. So the tangents over here, they will be intersecting at some angle A. That angle is what we look for. And of course, A times of mu minus 1, that's our deviation. So that's why we're looking for this thing. Now, their thing is h upon, okay, mu minus 1 is involved in the focal length. I guess that's why we're doing it. So, angle, what is the angle over here? These are the tangents, of course. And it's at h from this, right? So it's h over here. Well, this is like a very far away point, and this is our radius of curvature r. Yeah. Now this being h, this is being h as well, right? So you can say, right, this angle is approximately h upon r, because you know paraxial rays and everything. And if that angle is approximately h upon r, call this in theta. This will be like 90 minus theta. So, and guess what? You can just split it halfway, right? You can split it into half, this triangle into half. And now this triangle is similar to that triangle. So this angle, this was theta already. This is also going to be just theta. Call this theta 1, you know. So theta 1, and then this is going to be theta 2. So your A is just theta 1 plus theta 2. Now I'm doing this for a convex lens. Yeah, you get the idea. You get the idea. Right? Yeah, so your A is just theta 1 plus theta 2, but that's just equal to h upon r1 plus h upon r2. Now, these r1, r2 are positive values. If we want to use this for a general case, we'll first of all have to do some sign convention. So, r1 is in this case positive, r2 in this case is like negative. So, you will have negative h upon r2. And yeah, so with proper signs, this should happen. And then I know, I don't like doing this, but we'll just say it will extend to all kinds of, you know, lenses and everything. I hate doing this. Just hate that. Fine. Isn't there some better way of doing it? So when R is positive, right? When this guy hits like this angle, so at height h from where it's hitting, right? This angle theta 1, we'll just say the angle between this tangent and the normal. So going from the tangent to the normal, so in this direction, that's anti-clockwise, right? So we'll say it's positive. It's positive theta 1. So you just say theta is equal to h upon r for any surface, right? So in this case, r is the signed quantity, and h is also actually signed quantity. So it's in anti-clockwise and stuff, right? Yeah. So your anti-clockwise angles, like, of course. And what happens if your h is actually negative? Then this should turn out to be negative for a positive r. So if you have rays going over here or something, it's gonna be like this. So now so that from the tangent to the normal, yeah, you're going in clockwise directions, always negative. Right. And then of course your deviation will also be the different than what it originally was, right? So originally, if you're deviating like this, now it's other kind of, so it's inverted prism. It's gonna deviate like that. So your deviation also, yeah. And then in this particular case, your deviation is it upwards or wait, what? Is it upwards or not? Uh, oh god. Sorry, is it anti-clockwise or not? So for a prism, when you go like this, right? Your deviation is something like this, right? That's what we did it for. Yes. So it's going to be clockwise deviation of. So you can just, I mean, add a negative over here to get the thing in anti-clockwise sense. So now you've got theta in anti-clockwise sense is h upon r, but then you can do the same thing for this. Just now its radius is negative, but doesn't matter because still it's going to work. And then this makes sense because so if you have, so from this tangent to this normal, uh, you have theta 1, and then you got from this tangent to that normal, you have theta 2. So what's this going to be? Theta 1 minus theta 2, of course. That is the anti-clockwise A value, right? Yeah, that's right. So your A value is really just not this, it's theta 1 minus theta 2 actually in proper sign convention. So there we go. Now I'm doing this for a general case. Exactly. So for general case as well, it's gonna work, except you have to add this negative to get it clockwise, or you can just specify it's clockwise only, right? This is the sign quantity in clockwise direction. However, that works. Perfect. Yeah, and then yeah, mu minus 1 times all of this stuff. Guess what? So h times minus 1 times all of this stuff. 1 upon r minus 1 upon 2. Guess what? This thing is just the focal length. Boom. This h times the focal length, sorry, 1 upon the focal length. So h upon the focal length in clockwise sense, of course, that's our deviation. So remember, it's always going to be clockwise. And then what did they do? What did they do? In angle OAI, where is it? Where's I? Okay. Yeah, just some geometry. Not gonna do that. Not going to do that. Oh, so you just found out where the image is going to be. Oh, huh. Right. And then they approximated angles using tan of that angle and then found out deviation. That's also understandable. I think that's actually better than this method. Yeah. Hey, whatever. Next question. Dispersive power of a lens. Oh, I'm not gonna do this. I don't want to do all of this. Okay, whatever it does. So focal length is different for different. Okay, fine. Oh, so now you have a formula for deviation, and right, that's why focal length is going to be different because mu is going to be different, right? Okay, fine. So once again, omega is just a deviation in what do we call it? The red and yellow. Yes, so the difference of that deviation upon the deviation in yellow, sorry, red and violet, and this is upon the deviation in yellow. But in this case, it's different. It's focal length, but the deviation is inversely proportional to focal length, and then it's this. Why? I don't know. I mean, for prism it was different, and now it's this. Ugh. Thin lenses in contact. I mean, okay, this is not gonna do that. So, oh yeah, P1, P2, whatever. Why are they stressing so much on this chromatic aberration stuff? Will we actually be using this anywhere? Is it even in our syllabus? Okay. Yeah, well, I don't know. Whenever I'll see a question about this, I will refer back to this and read it at that time. I won't do it now. Oh, come on. Why? I'm gonna skip this. They're just torturing me like that. Separated by distance, the combination can't be reduced to a single thin lens. Rather, the combination reduces to a thick lens. However, in the special case when the object is placed at infinity, right, the combination is reduced to a thin lens. The focal length of the thin lens is given by this thing. Fine, whatever. Yeah. So what I'm saying, position of the equivalent lens is this much behind the second lens. Okay, so this is all of this is just for very small. So in other words, with very large magnitude values of u, right? That should work. Yeah. So for very large u values, what should happen? So first of all, the image will constantly be formed at the focus, right? Yeah, doesn't matter how it's gonna be. So we're gonna form the focus for sure. So you have something at very far away value. It's like it's gonna form at the focus, and now you got another thick lens. Sorry, another thin lens. Now this distance is like d. That's what you're saying. So d minus of not called focal length of focal length objective focal length I. I know. Why do this? But I'm gonna do it anyway. So this is like d minus f naught. Yeah, that's our negative u value now. So now you just have 1 upon v. So negative 1 upon 1 upon d minus f naught. This is equal to 1 upon fe. So there we go. You have 1 upon v value is just like 1 upon fe minus that's like plus 1 upon f naught plus t or something. That's not nice at all. Okay, and you're saying so position of the equivalent is like df upon f1, which is this thing, and that upon f1. Huh? So you have to change your v such that you get a more symmetric form, I guess. Uh-huh. Now what do I do with it? It's not making any sense now. You have 1 upon f1 plus 1 upon f2 minus d upon f1 f2. Why? Where did this thing go? I mean, of course it changed it, so that's why. Right, so it's sent depending on where you actually place this thickness, that will, yeah, that's gonna do the thing. So you are saying position of the equivalence if you place it at df upon f1, then actually focal length that you're looking for is just well v minus df upon f1, right? Behind the second lens. Oh, sorry. This v we calculate for this guy. So, oh, behind the second. You mean this? Yeah. Okay, okay, okay. Understandable, understandable. Click plus actually in that case. Right. So this is what our focal length that we're looking for is. So 1 upon that will just be 1 upon v plus df upon f1. So like 1 upon f1 v plus df. What is this? It's crazy. Oh, you'll have to figure out v, I guess. So this will be, oh, using f1, f2, I'm gonna use that as well. So eyepiece is like 2, I think. That's 1. This will be equal to f1 plus t plus f2 upon f2 times f1 plus t. So v is just f2 times f1 plus t, and that upon f1 plus f2 times t. Sorry, plus t. What am I doing? Yeah, that's right. Now this plus df upon f1. Why just f1? I don't get it. What's that going to do? Why are you doing it? Behind the second lens. What? What is this? Not making sense. Why would you want this? Oh, you got this capital F over there. Huh. Wait, what? Oh wait, what do you mean? So that just means like a capital F, which is just equal to this thing. So this means like V should be equal to, yeah, capital F times 1 minus d upon f1. So that's going to be f1 minus d. Is that correct though? Yeah, this is equal to capital F. So minus, right? That is the thing. So, oh, it's negative. What am I doing? It's supposed to be negative. Oh, that's why everything went wrong. It's negative right there. It's going to be negative right here and right here as well. It's f1 minus d, and that upon uh, f1, right? So when you, yeah, so your v should be like this. So by comparison, it should be negative over here. So by comparison, your capital F upon F1, that should be equal to all of this stuff. So capital F is equal to F1, F2 upon F1 plus F2 minus D. So 1 upon F would definitely be this thing, right? But all in all, why would you want to do this? Why not just take it as two separate lenses? This doesn't make any sense. Why this weird definition? Why do you even need a focal point for this combination, right? It's not even useful. And then once again, chromatic aberration, whatever. Silvering of it. Oh yeah, I actually made a formula for this thing. Right. So you can get this thing. Oh, first of all, in chapter 12. Parallel beam of light. First of all, erase this thing. Parallel beam of light is incident on system of two convex lenses of focal length 20 centimeter and 10 centimeter. Okay. Oh, it's from that question. Should this two? Okay, distance between the two lenses that the rays after refraction from both the lenses pass undeviated. That is, these become parallel, right? Once again after this refract. Oh, so this guy's focus must match with this guy's focus. So the distance between them should just be focal length 1 plus focal length 2. So it's gonna be 30 centimeters. That was easy. Yeah. Okay. Then you got third, silvering of lenses. So yeah, I made a whole formula for that. But honestly, I don't think that formula is so useful because in the end, you just need to know what mu is. Okay, if they actually gave us the focal length first and then told us to use silver on of the surfaces, then yeah, your formula might be useful, right? So once again, what is that formula? So you got this object over here. You have this lens and then you got mirror over here, whatever. So one surface, other surface. This is I don't know, if it is n, this might be 1, right? It's taking it to be 1, you can take it to be anything you want, right? And then what we'll say is, okay, for this guy, so first of all, what's the final index of the image? It's going to be negative 1 because it's going to come back, right? So negative 1 upon v and then minus 1 upon u. So because this is 1, so minus 1 upon u, and that's equal to, this is mu1. So what's happening is that first for this guy, you should just have mu2 minus mu1 so n minus 1 and that upon r1. Yes. Now for this case, you might even have something like this, right? So we'll just take r1, r2 to be signed quantities. For this guy, what's happening is that you are going from this medium of n refractive index to a medium of negative n refractive index, which is of course this is just this medium, but you're going opposite, and that's why final initial is going to be minus 2n. And minus 2n upon r2 is what we look for, right? The last term is we are going from here to here, so it's going from minus n to minus 1. So final initial is just n minus 1. So plus n minus 1 upon r1. So it should be 2 times of that. Yes, this is our, what do we call it? What was I going to call it? Right, this is our formula. So just this is like 1 upon v plus 1 upon u is equal to 2n upon r2 minus 2 times of n minus 1 upon r2. Now, wouldn't it be nice if this was somehow written as focal length? So what we can do is just write like 2n minus, no, yeah, whatever. So it's got 2 times of n minus 1 upon r, it's supposed to be r1 over here, upon r2, right? And then you got plus 2 upon r2, and then minus 2 n minus 1 upon, yeah, all that stuff. So look at this, it's just the 1 upon the focal length of the mirror, right, of this mirror. And look at this, minus 2 n minus 1, then you got 1 upon r1, sorry, yeah, 1 upon r1 minus 1 upon r2. Look at this thing, it's just the focal length of the lens. So it's going to be 1 upon focal length mirror minus 2 upon focal length lens, right? That's what 1 upon u plus 1 upon v will be. Right? So that's silvering of lens. But did they give us the formula? Oh yeah, they did actually. So 2 power of the lens plus power of the mirror. Huh? But power of the mirror is just negative 1 upon f. So like negative power of the mirror minus 2 power of the lens. I don't know what they're doing over here. Why would you do this thing? Yeah. Huh. Or it shouldn't be like negative of that, because when u is going to be negative infinity, 1 upon v is this thing, so 1 upon f basically, f effective is this thing, so your power is really just negative power of mirror, negative 2 power of the lens. I don't know why would they do this, like positive? No, it's not positive. Huh? Determine the position of the image, use the mirror formula with equivalent focal length. Equivalent focal length. Wait, what? Now it's just, how could they do this? It's clearly not 2 upon FL minus 1 upon FM. No, it's just, okay, what if somehow your lens was having the same medium as the surrounding medium? So in that case, this whole term would not be there, so just be 1 upon FM as expected, right? Yeah. And they are saying that's not correct. They're saying minus 1 upon FM should be over here, which is just wrong. You can see that it's just wrong, right? Yeah. This is not correct. If they are saying this is the power and then 1 upon the power is the focal length, no, 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 no. That's not how it's supposed to be. Oh, wait, what? PM is equal to 1 upon. Why? And why didn't you just do negative 2 and what? No, okay, this is wrong at multiple levels, it seems. Oh, so that's why you took. But still, it's like just. It's not. It's supposed to be negative 2 upon the. So, where did that go? Where is the negative 2 factor? I don't know. Hmm. Anyway, next, what do you have? So, illustration. Where is it? Cutting of lens. This becomes this thing. Transversely, you mean like, okay, this got cut with that. So it's equiconcave lens. Concave, you mean convex. So it's, the diagram says convex. That's what it is. Yeah, I mean that other term just goes away because like R2 would just be 0, boom. It's going to be, yeah, 2 times the focal length. Yeah, whatever. Not a big deal. Why would more than one image? It's the same lens, just a bit of it is like removed or cut and separated, whatever. 2 images are formed as one. What? What are you doing? Object is placed at a distance 0.3 from a convex lens. Oh, okay. In the y coordinates. Oh, yeah. So this guy's y coordinate, I think it changes, but should it not change because its optic center is just gone? What? It shouldn't behave like normal lens. Oh, these are displaced. Ah, right. That's why this is happening. Both these guys have the right. So I have optic center is somewhere over here. So for this guy's y coordinate is negative. This guy's according to this guy's y coordinate is positive. Both having same magnitude, and that's why this happens. Okay. And that's why these arrows are not actually pointing to it. Okay, that's what's created the distance. X coordinate is still the same though. Okay, now I got it. By displacement method. Ah, so practical calculation. Nah, not interested in that. What's this? Yeah, whatever. Let's not do this thing. Same thing, compensation. Right, where's the exercise? Where is the exercise? Oh, now I just have exercise 1. So all the algebra exercises are just done now. Fine. So this is it. I think in next video I'll start this thing. So how long is it going to be? Oh, it's going to be really long. Okay, fine. We'll see if we can do it. Fine. So I'll see you guys in the next video. Bye.